This week, we got a retrospective on the work we did with Centrifuge, and this also marks our release of our first article written by Nicanor here in the chat with us. And this article talks about some of our insights into the part 1 out of 2 of the work we did with Centrifuge. So I'm gonna share my screen. Let me know when you see it. Anybody unmute? Say yes. Say yes if you see the Recon homepage.
Yes.
Awesome, thank you. And this is the retrospective of the work we did with Centrifuge back towards the end of February. And as I like to say, the best testimonial is the customer coming back. So this was part 1, and then there's also going to be a discussion about part 2. We will release the article at the end of the office hours, so it will be on Twitter, it will be live, and these office hours will talk about a couple of techniques we developed during the engagement, as well as a couple of code bases we are about to open source, so you can use them in future invariant work. And then lastly, at the end, I'm also gonna tease why there's no part 2, and also what you can do as a security researcher to, I guess, get an edge as to why part 2 is not live yet. And so, first of all, let's talk about what Centrifuge looks like. They actually have this really awesome chart. And by the way, we, as Recon, we come after a contest done with Sherlock, or actually with Code Arena, and then a Spirit review. So this code base is already fairly mature. It's open source at Centrifuge Liquidity Pools. Anybody can check it with, I think it's AGPL license. And so the foundational aspect around how Centrifuge works is this. I'm gonna go in the mirror and I'm gonna start sketching. But at the base level, we have what are called liquidity pools. And then we have tranche tokens, which we can think of as a receipt to the liquidity pool. We then have investment manager and pool manager. And we'll talk about them a bit more, but basically you can think of them as the, let's call it the admin or the implementation side of this. And then we have the gateway and the routers, which you can think of as the, I guess I'll type EVM, but fundamentally these are cross-chain messaging applications that can have an impact on behavior. And so one of the most important things in invariant testing is to figure out what you want to test. It sounds really dumb, but as a coder, as a programmer, it's really easy to just look at something, look at a code base, and perhaps focus on coverage or focus on scaffolding or refactor it. So there's always work that you can do. But as a security researcher, you instead want to focus on meaningful things that you can check for. And so one of the most important things in this engagement was actually learning about the code base. And we'll talk about that as we talk about part 2. So instead, in part one, our main goal was getting to coverage. And then thinking about meaningful permutations, which means the idea of having multiple different changes to the code base or changes to the settings so that we can have coverage that is not just a line-by-line coverage, but also a logical coverage, as in we're testing different combinations of different settings. And then the last thing was focusing on maintainability. What's the point of writing a lot of code that is crappy and that is going to get deleted or dropped or not used? There really is no wisdom there. And our main goal at Recon is instead to get people to use invariant tests. Basically, at the end of every day, we want to write you a good set of tests and good setup, and then you do your work, and then at the end of the day, you let it cook, and then the day after, you see whether something broke or not. And so that's kind of our philosophy. And going back to how Centrifuge works, you would have what are called currencies. I'm just going to drop the $sign here. And so you would have a currency, you deposit a currency in the liquidity pool. The liquidity pool is basically just a interface or just a effectively, this is a pattern that is similar to delegate calling to the investment manager. But at the end of the day, you can think of the liquidity pool plus the investment manager as the actual liquidity pool, meaning the proxy that you talk to and the implementation. And then the pool manager is more of a configuration contract. And so you will drop your currency, you would drop it in the liquidity pool figures out what to do based on the investment manager, and then your message gets broadcasted on a different chain called the centrifuge chain. And then the centrifuge chain would eventually have a callback and fulfill the request. Do we have any questions so far on the centrifuge architecture? Feel free to stop me. Otherwise, I'll go back to this if you have questions. But fundamentally, if you're confused a little bit, that's also how I was. And that's because even the power that we brought with our own tooling is that when you get started with a code base, let me see if we have it here. Maybe we don't, because it's, oh, there we go. Like, it's actually easier to just get started and fuzz something. So in this case, we would have fuzzed the liquidity pool, perhaps the pool manager, the investment manager, right? We could have just gotten something like this, and we were able to very quickly get to a decent coverage simply by doing this. But at the same time, the devil is in the detail, especially when it comes to invariant testing, because you want to test for meaningful aspects. And so the first interesting detail about this currency liquidity pool combination is that you can actually have multiple currencies per liquidity pool. And so you can have one liquidity pool, but you can have many currencies, or you can have many liquidity pools that each of them has many currencies. And the only thing that kind of ties this together is that for each currency and for each liquidity pool, you would also have a different tranche token. And so, surprisingly enough, we basically had this differentiation between what a liquidity pool is and what a tranche is, where a tranche will basically be a different type of a risk applied to the same liquidity pool. So it's basically a different section of the same underlying strategy. And you could enter one of those strategies through different currencies. And as I said, the flow will be an asynchronous flow of depositing your currency in the liquidity pool, having the, let's call it admin, the centrifuge chain, somehow have a callback, and then we would effectively mint the tokens back for the mint and redeem, or rather for the mint and deposit functions of ER6, 46, 26. And then we also add a few extra tracking contracts. And so as we thought about this idea of the tranche token, the liquidity pool, and the different chain, we had to go for our first compromise. And the wisdom in invariant testing is knowing when to compromise on what. And so the choice that we made was to focus on this area of the code base and ignore this area of the code base, which means that if you look at it from their original chart, we mocked all of our callbacks here because adding this as part of our original tester would have forced us to spend tens of hours in just getting that to work instead of focusing on what was meaningful at the time, which was this relation of currencies, liquidity, and tranche tokens. And so that's one of the first decisions we made, is we spoke with them, with the Centrifuge team, and we looked at the properties they wrote because we ran them through the invariant writing exercise, which is the idea of talking about different types of invariants, from stateful invariants, state transitions, stateful fuzz, or perhaps doomsday invariants or dust invariants. And basically, after going through all of the possibilities and talking through them and having the team write the initial specification, because obviously the team has worked with this code base a lot longer than us, so they're going to be a lot better than us at the beginning especially. And so it was clear that there was this division between, let's call it the more admin focused, trusted stuff, which will be the centrifuge chain, and the more, let's call it vault-like system of the tranche token, liquidity pool, and multiple currency. And so we made that simple decision, and that simple decision dictated the fact that we had a lower surface area, so we could get to coverage faster, and we could also get to meaningful coverage faster. And so as you can read in the article a little bit more, the main initial goal was simply to write basic stateful fuzzes of redeeming, depositing, getting that callback, requesting a redeem, requesting a deposit, requesting a withdraw, etc., as a means to quickly get there. And so a great example here of something that is great software engineering advice, but it's actually kind of bad pragmatic developer advice, is the idea of having reusable code a little too early. So when your code base is done and you've achieved 100% coverage, you have 100% logical coverage, you're satisfied with the coverage, with the idea, with the properties, etc., then you can think about making the code easier to maintain. But at the beginning, if you don't even know whether the code works and you just need to make it work, then your workflow will always look a little bit like this. You're going to just write some stuff, and then you're going to run Medusa, and you're going to look at the coverage report, where the coverage report here, green means that the line was called, green means this line was called, and then red means that this line wasn't called. And the interesting aspect about this is that the fact that this line is red and this line is green doesn't actually mean that this line reverted here, because get balance could be a function that has like 20 lines. And so in order for us to determine what went wrong, we actually would have to go and check the implementation and review it. And so what happens if you get this image here and you replace it with some code like this one, where you just get balance internal? The result that you will get is that because you're reusing the same code, then as long as at least one time this code works and it compiles, then your coverage report will actually give you all green lines. And so that means that even though in this section you're getting a revert, now it actually becomes impossible to debug this line because you're not gonna know why it reverted. And so for how dumb it may sound, sometimes it's better to just rewrite a piece of code so that you can see where the fuzzer gets stuck and where the coverage is pointing you towards the fact that the fuzzer is unable to continue. And so premature optimization really is the root of all evil. And this is an example of dry being a problem, right? You wouldn't want to repeat yourself by getting the balance again. And yet, if the balance reverts, now you actually created more problems by trying to be a little too smart, a little too early. And so that's the first advice, is when you are bootstrapping invariants, you don't want to be too smart too early. You want to be wise to know that eventually you'll optimize, but there's no reason to optimize on day 1 or day 3 or day 5. You can optimize on week 2, week 3, week 4, once you've already established a base level of coverage. And so this is something I hope you can think about, is that every engineer, like the mark of a poor engineer is the engineer trying to be too smart or smarter than they need to. It actually is smarter to just do less and then see what happens, because we never run out of work in this line of industry. In this industry, there's always more, and so that's one of the main considerations. The second consideration here, which I already explained earlier, was about only fuzzing what's necessary. So again, let's just look at the system. We already have enough issues. Our engagement is only 1 week and a half. Why would we spend multiple days trying to set up all of this messaging system, there's redundancy so that they can send messages? Why would we spend time with ABI.encode when we can just write our handlers to call stuff directly? That's another example of there really is no rule that says that you have to have one invariant tester. I don't know why many projects think that you're supposed to have one giant tester that takes forever to do something. I feel like, especially at the beginning, especially to do like an 80% that gives like the 20% that gives you the 80%, like a Pareto principle approach, is to just spin up a new tester anytime you need to, get to that coverage, and then eventually you can consider incorporating everything into one. So that's something to keep in mind. And then the third lesson, which is the key piece of the first engagement, has to do with finding a way to test multiple permutations without going insane. And so let's go back to the discussion here around how complex and how basically we really choose our own difficulty here of how miserable we want to be by deciding how to implement multiple currencies, the liquidity pools, and multiple tranche tokens. And so I want to show you how I did it in a way that actually didn't make me miserable, by trying to be a bit clever about what to do and by taking a trade-off that allowed us to get to a high coverage while at the same time keeping the code simple. And so let's start by looking at the facts. The facts are going to be that if you have multiple currencies, multiple tranche tokens, and multiple liquidity pools, then you will be tempted to simply have some sort of a multiplicative effect of saying that you need to have those currencies, you need to have those tranche tokens, you need to have those liquidity pools. And there really is nothing wrong with this until you start to, I guess, try and implement it. So maybe let's go on a, I guess, let's see if I can find a test that shows you the nightmare mode that you committed yourself to just by choosing to do this multiplicative effect instead of looking for a simpler solution. So it's gonna take me a minute to find the code base. I guess it's gonna be in base test. Let's see what we got here. Setup, mock router, test router, push, blah, blah, labeling of various stuff. And then we have, let's see, we have deploy vault. And you can see deploy vault means that you get a tranche token, you deploy a tranche, and then to add a tranche, you actually, there you go, you need to add a push. So let's look at this from this perspective of how you will have to set it up. Basically, you will need to register a asset ID, which is basically a currency. So you will actually have to first register a pool ID. So that's the first step, register a pool ID. Then you would have to add a tranche to the pool ID, which means that now we have a, we don't have a tranche token, but we have a tranche of the pool. So we have a risk section of the pool. So now we have, let's call it the TID, the tranche ID. Then you would have to enable the asset on the tranche. Then you would have to deploy the tranche, which is not the same as deploying the, or maybe it is the same as deploying the liquidity pool. And so basically, let's stop here. But basically, we had to perform 1, 2, 3, 4, 5 steps, let's say 5 steps to achieve that. And so a, I guess, rigorous, skilled fuzzer will tell you that since it takes you 5 steps, you're not supposed to have like a function here that just takes all the 5 steps. You're actually supposed to separate them into, function A, function B, etc., and just wait for the fuzzer to find that coverage. But if you think about it, there is nothing meaningful about having the fuzzer waste time before there's one liquidity pool deployed, because we are not here to test ERC20 tokens. We're not here to test the centrifuge chain because we already took the trade-off of not fuzzing it. So there really is no benefit in adding all of that extra randomness. And so what we did is we instead had a single function called deploy new token pool and tranche, so that we had a way on day one to have a good level of coverage, which means that instead of waiting 4 hours looking at the fuzzer for the fuzzer to figure out that he has to do this order, we would just have the fuzzer press a button and deploy the entire thing so that we would have a level of coverage. And now the clear downside with this decision is that you're missing all of these possible permutations. So doing this and stopping is not ideal. I'm not telling you that that was the best move. I'm telling you that that was a good move to get started. And so over time, this function, deploy new pool, new token pool and tranche, evolved. You can see that the first thing I added was this require has done a deploy, which basically will make it so that once the first deployment was done, it will stop deploying new tokens. And that was just a way to ensure that only one pool, one liquidity pool was deployed so that we could just check it and verify that there were no weird reverts, that our coverage would work, etc. And so the second we reach that coverage, we can get rid of this line, or we can also just not set it by simply having this flag, this Recon flag of not setting the has done a deploy. So that means that now we went from deploying one of these combinations to many of these single combinations. And so by doing that, we found almost a dumb, in a way, but at the same time fast and simple way to test for multiple combinations without needing to take these multiplicative complexity. And that's because as long as you add randomness on the decimals for the currency token and for the tranche token, then over time, even though you're not testing a pool with multiple tokens in the same pool with different shares or rather decimals in the same pool, so that's still missing. But in spite of that, having this linear deployment means that now you can still test for multiple combinations in the same run with basically zero effort. Like the easiness of setting that up is basically really high because you just set this function that sets all of your targets, and then anytime you write your targets, you can just write them in the singular. You don't have to think about the fact that there's multiple of them because you made the switch, the target switching function, you made it into a separate function. And so all of our Medusa traces and Echidna traces would always start with these deploy new token pool and tranche, simply because that's how you get started. That was like the setup function. And then if the fuzzer needed more versions of the tranche and currencies, then it would simply spam them until it would find the decimals that it needed. And so that's an example of taking some trade-offs as a means to make it easy. And so that's exactly what this chart shows you. It shows you that this way we were able to quickly and easily build something that was easy to understand, easy to maintain, and easy to reason around, while at the same time reaching a high degree of coverage. And then in part 2, we can also look at what we did in order to actually add the multiple combinations. And we can also talk about how that wasn't necessarily, wasn't even particularly necessary. And so those are the 3 main lessons from the first engagement. Purposefully choosing what to test and what to not test, and being aware of the trade-offs. Being wise about not prematurely refactoring and prematurely over-optimizing the code. And then lastly, making the code easy to maintain by writing simple code that actually has a big impact in your coverage and in your tests. So the last thing that I want to mention has to do with an idea that will develop further over time as we continue to do these office hours, but it's the idea of the story and the idea of the tests. Before I get there, let me see if there's any quick note or question in the chat. If you want to drop a question or you want to ask it, feel free to unmute. I'm happy to answer them. And in the meantime, I'm going to talk about this idea of the story and this idea of testing. And so in a few minutes, I'll reveal why we're not doing part 2 and when part 2 is going to drop. And so stay tuned. We're going to give you some real alpha. But the main idea I wanted to mention with for example, the centrifuge engagement is how in wanting to have a simple code base and having simple testers, something that can happen is that you may write some properties that end up duplicating a function. An example will be saying that you have to deposit just to increase what I would call the story. So the story meaning that these are part of your sequence of operations. Whereas maybe you would have like a, I don't know, a classic arbitrage test will be that you deposit and withdraw, and you verify that both amounts don't cause a gain. And so this will be the arbitrage doomsday tester. This is something that we do, arbitrage doomsday tester. So that would be literally a separate fuzz test that we will write, and then this would instead be the deposit handler, because this is bringing up the story, whereas that one is trying multiple things. And so if you start to think about these handlers as the same thing, then the second you end up needing a storage variable like a ghost variable or something, you're basically ruining your life. Like, you are creating so much extra work for yourself, and it's completely needless. And so the way I like to solve this is by thinking about the story and thinking about the tests. And so a story handler is a handler that exists for the sole purpose of changing the state. That's basically what it does. It deposits, so I need to increase the counter for the deposits, and the balances of tokens have increased. And so that's why the deposit function exists in the handlers. Whereas an arbitrage doomsday tester is about checking that at any time in the story, I cannot deposit and withdraw, and that's not gonna create a arbitrage opportunity. And so the idea that you will want to track the story for this and for this doesn't really make sense, because if you wanted to track the story for this and that, you will simply have a handler for deposit and a handler for withdraw, and Echidna and Medusa are completely capable of doing that, so you don't have to enforce it. And instead, what I opted to do in order to keep my own sanity and my own productivity was to, once I decided that a test was a test handler and not a story handler, I introduced the idea of the call, test, and undo library. And so this is an open source library that we open sourcing thanks to the work we've done with Centrifuge. And it's a very simple file that fundamentally can help you achieve this exact goal of creating a completely consistent do and revert behavior for systems that do not support snapshot and revert to. Obviously, if you're using Foundry, all I'm about to show is absolutely unnecessary, but Recon doesn't just support Foundry, it supports Medusa, Echidna, and Halmos. And so we have to write something that works for all of them, and this is what works for all of them. So we have an abstract contract, we have an external function that receives some call data. This external function will call this own address with the call data, and then if the transaction fails through a revert, it's going to actually return true. And that's how most invariant tests are set up, that a revert does not cause a failure in the test. You don't fail on revert, you fail on failed assert. And the way in which we fail the assertion here is by returning false as part of our return data. And so that's why the return data is then interpreted as a Boolean, although we do something funny about Solidity, which is that you can actually return, quote unquote, return a Boolean by actually reverting it. So we revert the Boolean, and then our internal function, which is the function you're supposed to use, called do, test, and return result, will catch that revert reason and will return it, which means that through using this, and I'll show you an example in a moment, I coded a test in the repo for you to see the example, but this means that now, anytime we are building the story, we can just focus on the story, focus on the ghost variables, focus on the storage, etc. And then anytime we need a test that is gonna make our life miserable, and we don't wanna add it to the story, we just add this extra piece, and now we can add as many tests as we want. They're going to be performed randomly by following the same logic as Medusa and Echidna, as they always do. But now they're not going to interfere with the story, which means that most of our code is going to be a lot easier to maintain because you're not going to have to update a trillion ghost variables just because you decided to add one extra test or you needed to check for a function reverting or a function not being available in some way. And so let's look at an example of doing this. You can see it here in the demo t.sol, and fundamentally I have a test. So you will refactor your test instead of failing the assertion to instead return true or false. That's the main change in code. And now we have a test that, let's say we want to verify that this never overflows, for example, and we know it will never because the counter is 0. But fundamentally, we will call it. We call it with a new amount. We know the storage value is being changed. And yet, because we do test and return result, we will return true, the test will pass, but the storage value is no longer changed. So that means that going back to the idea, you can focus on having your atomic story pieces and tracking them as accurately as you need. But now you have the freedom to create more complex tests that will not drive you insane in having to track all of these extra storage changes because of all of your ghost variables. So hopefully that saves you time and it allows you to build safer systems where, again, you separate the story, the atomic elements, and instead you have the more complex testers, but you treat them as such, as one-off testers that do not interact with the story. And this is being open sourced as GPL2 on Recon Fuzz at Recon Fuzz call test undo. And obviously you can install it via forge install Recon Fuzz call test undo as well. So that's pretty much it from my presentation. Let's give you some alpha. If you guys want to ask a few questions, feel free to do so. The reason why, or rather the time at which we will post part 2 is because Centrifuge will do a security contest. And so right before they do their security contest, we will host a workshop with them. We will go over part 2. We'll open source the invariant testing in our style. So something that should be familiar with you guys if you've been at our office hours. And that means that in having used Recon and having understood these few ideas, you'll see a lot of these similar ideas when we open source the Centrifuge invariant tests. And so stay tuned, because as soon as they finalize their code base, they will want to do a security contest, and we will host a workshop with them, again, in which we'll publish part 2, show you some of our secrets in terms of coverage, in terms of the story, in terms of the properties that we wrote, and in terms of the other libraries that we're going to open source. And then they will have a contest, which means that knowing invariants can also give you an edge to win that contest, which will happen as soon as the second version of Liquidity Pools is ready to go. With that said, if you want to ask a question, feel free to. Otherwise, thank you for joining me today at the Recon office hours, and we'll see you next Thursday.